Now, what we need to talk about is what statisticians see when they look at a histogram. And the first thing to do is actually to get a general sense of what this histogram shape is like, the shape of this distribution. And to do that, I want to draw a smooth curve on the histogram. So just, you can imagine doing this with a pencil, kind of seeing this histogram and kind of trying to trace out the top edge of the bars, but in a nice smooth way. So here, let me try this. There we go. Okay, up and down and up and down and down and up there. Okay, so I see this black line, and you can see it kind of follows the flow of the histogram as it is, and I look at that and I think, oh, that's kind of interesting. I could see kind of two bumps here that I got, and maybe a little bump down here on the right hand side, and those we'll find out are very important statistically, and so we will use those for good purpose. But before we do that, I want to look at a different data set. Here is this is a data set from our book. There are 45 golf courses that they collected total range length on. So that is these golf courses, right? Each hole has a certain distance in feet, and what they've done is added up the 18 holes distances for each golf course, over 45 golf courses. So some golf courses have very long ranges, like 6,000 feet. And if you play every hole, you will walk 6,000 feet, and some have less lengthy courses. So is there some kind of pattern? And what I'll do is I'll get a histogram, and indeed it looks like there's sort of a lot of the courses. Notice 10 of them have somewhere between, and it looks like these are 200 feet bends. So this bend right here is from 5,800 to 6,000, and 10 courses have lengths that long, and that's actually the most prominent one. There are some that are shorter and some that are taller. There are some that are much shorter. There are a few, looks like one, that is just a bit more than 5,000 feet in length. Okay, and there are on the other side a couple that are quite long. That 60 looks like it's around 66,000. I'm sorry, 6,600 feet long. So that's looks like where the longest courses are. So I can see some details here about the histogram. But again, what I want is a kind of a smooth curve to capture its shape. So let me trace this out and get a kind of a smooth curve, and that's kind of a neat looking thing. But it gives me a general picture of what that histogram is hinting at. Here's another one. This is another data set, and we'll look at these data sets again, but I'm introducing the beginning. These are math scores, average math achievement scores, I think for 7th or 8th graders, by state. So you see Alabama had an average score of 225, Alaska has an average score of 236, so forth and so on. So I want to look at the distribution of those. So here's the histogram of them. You see that actually most of the states, it looks like 15 were in this bin and 15 were in this bin, and so 30 of the states were somewhere between 235 and 245 in terms of scores, but there are some that are a little bit higher and some that are lower. Let me draw the nice smooth curve. Okay, you can see it goes up on that side and it goes down pretty quickly to get down to 0 on that side, and that gives me the shape of that distribution. One more. This is another data set from our book where they took a look at the movies that were widely released in 2005. There were 120 of them, and they looked at their budget, how many millions of dollars were spent to make the movie. And I haven't shown the data table, but we've got the histogram over here, and we can see that the tallest bar were well over 40. Movies were somewhere in the 30 to 40 $1 million range. Some were more expensive, $50 million, and some were more expensive than that, $100 million, and some were really expensive, way out here, 150 million or so dollars to make these couple of movies, a couple three movies out on this side. But again, what I want is a nice smooth curve, and you can see I get this nice curve that goes way up at the beginning and then kind of tails out over onto the right. These curves, these smooth curves, are supposed to point out the features that we want to look at. Statisticians, when they look at a histogram, are looking for a couple of things, specific things. So one of the things we look for is our bumps, as we saw in this beginning one, the shoe size. This is the shoe size data for my students, and we saw when we drew this smooth curve that we kind of had these two bumps here, okay, and we have a name for those bumps. Those are called modes. They are bars or areas in the graph that are kind of higher than their neighbors, right? Right. And I say significantly higher because, if it's just a little bit higher, one or two people, then maybe that's not really, that's just happenstance. It's not really something we should pay attention to. But if there's quite a few, and it looks like there's this bar to this bar jumps up quite a bit, as this bar by its neighbors. What we'll say is that we have these two hills, these two bumps, and we call those modes, right? These two things are modes. We actually talk about the distribution in whole by saying how many modes. If it has one mode, one hill, then we say it's a unimodal distribution. If it has two modes, we'll say bimodal, like this one. This shoe size is bimodal. And then three or more modes, we'll just throw that into a category of multimodal, many modes. So when we see a mode in a statistical graph, we actually have something to say about that. We say, well, that's a big category, right? There's a big bar there, and so there's a lot of people in that. So that somehow that mode represents a typical or target value. So something that is predominant, right? That particular value. So in this case, like I said, 8 or 9. And in fact, in this case, I have shoe sizes in the 8s and 9s, and then also shoe sizes in the 10s that seem to be typical values. When I have multiple modes, what that usually means is that I have two unlike groups being thrown in together in the data, and they're kind of getting they behave differently with different typical values. So in this case, and this is a really great case because shoe sizes, it seems like I have two modes, one at 8 or 9 and then one at 10, 10 and a half. What could that be? What two groups could be causing that? And a pretty obvious answer is, oh yeah, men and women, right? So the women generally have shoe sizes around 8 or 9, and men generally have shoe sizes in the 10s, even that is even after we adjust for shoes that the shoe sizes are different for men and women, measured differently. But that notwithstanding, these two modes are there because there's one group in the data that are women, of course, with shoes around 8 or 9, right? And then another group of men with shoe sizes around 10. And so I see these two modes sort of popping out because of that. And that's actually quite, when a statistician sees two modes, they say, oh, look, there's two groups here, and let's get to the bottom of it. Another thing we look at when we look at a histogram is for symmetry. So when we have one mode, we can in some sense look at that one mode and then look to the left and to the right and say, well, does it look about the same on each side, right? Is there a symmetry around that center? And in this case, you can see if I draw a dotted line down the center, that on the two sides, it's not perfect. There's not a perfect symmetry, and we're never interested in perfect symmetry. But it's not bad either. The two sides of this histogram around that dashed line, pretty much the same. What this means is that in some sense this goal is the typical value is there's some that are bigger, some that are smaller, but they kind of spread out from the middle. So this, remember, is this graph is from the total length of the golf courses. And so what this is telling me is that there is, in some sense, a pretty typical length, right? About 6,000 feet for a golf course is a pretty good, maybe a little less, is a pretty good goal to shoot for. But some golf courses are made a little bit bigger, and so you get some to the right of that center line. And some golf courses are a little bit smaller, but it's kind of varying evenly on either side. And some courses are much longer, and some courses are much shorter, but varying evenly that way as well. So this symmetry tells me that these things spread out around the middle in a nice even way. And in fact, there's some examples of things that I think would probably be symmetric. Things like if I collected, hundreds of potato chip bags and weighed them, all of the same kind of potato chip, same kind of manufacturer and all that, I would bet that their distribution of their weight would be symmetric. Why? Well, because there's some target weight that Frito-Lay sits down and says the bag should be filled to this, and then some are a little bit smaller, some are a little bit bigger, but they kind of evenly spread around that target value. Other things that would be symmetric are things like heights of full-grown male elephants. I mean, that sounds crazy, but okay, let's tackle this first. First, I focused on male elephants because I wanted all the same gender, so we don't get any gender differences. And because if I put in the female elephants, then I might get a bimodal distribution. So I'll focus only on male elephants. I'll look at full-grown ones because if I included juvenile elephants, well, they're still growing, and so in some sense they'll throw off the analysis. So I want full-grown male elephants, and I'll look at their heights. Well, there's some predisposition for elephants to grow to a particular height, right? So that's the typical height. But some elephants grow a little bit taller than that, for genetics or because of what they eat and so forth. But at the same time, some elephants grow smaller than that. And they'll be evenly distributed around that middle value, that typical value that elephants grow to. So I would bet that heights of full-grown male elephants would actually be very symmetric, would have a very symmetric shape. And then the last one, amount of time to read a paragraph. I mean, there are only so many words in a paragraph. You give it to somebody to read, you time them, and then you do that over and over. The distribution of the time to read that paragraph, well, there's some kind of typical reading speed. A lot of people will read that rapidly, and at that speed. But there will be a few that will read faster, and there will be a few that will read slower. But that it will sort of spread out around that typical value to give me the symmetry in the distribution shape.